Okay, now the concept is Faraday's laws of electromagnetic induction. So what is this concept about? Electromagnetic induction. So here we are going to talk about inductor, inductance and induction in the system. Okay, so this Faraday's laws are two. The first law for Faraday's, so the Faraday's first law, what does it states? So this first law states that when the flux linking with the coil or circuit changes, an EMF is induced in it, or whenever a magnetic flux is cut by the conductor, an EMF is induced. So whatever it is, finally they are saying an EMF is induced in the conductor. So there is a coil. If you give a current, it will induce an EMF, means it will give you electromotive force, EMF, which is obviously can be referred as voltage as well. Okay, so it is giving an EMF. Okay, so that is what the first law is saying. Then what is the second law saying? So the second law is talking about the magnitude of this EMF induced. Okay, the EMF induced is directly proportional to the rate of change of flux linkage, or to the product of number of turns to the rate of change of flux linkage. Okay, first law, what it is saying, when a current is passed through the coil, it will induce an EMF, means it will give you an voltage. That voltage is nothing but directly proportional to flux with the change of current, because change of current will give change of flux, because current is inducing flux. The current is producing flux. That flux is inducing EMF, right? So EMF is nothing but the flux induced. The induced flux is with the rate of change, because current changes, flux changes. So EMF induced is directly proportional to the rate of change of flux, d by dt of phi. Same way, to remove the proportionality, we brought the number of turns, because number of the turns will decide the flux density also. So that's why n into d phi by dt. Okay, so here we are talking about Lenz's law. So the other concept we are talking about is Lenz's law. Sorry, what is this law stating? So this law states that the direction of this induced EMF is such that the current produced by it sets up a magnetic field opposing the motion of charge. So according to Lenz's law, always the EMF induced will be with a negative charge. Okay, so the Lenz's law talks about the negative charge. So the negative charge is because of the magnetic field opposing the motion of charge. Okay, so the produced is opposed by the motion, so that's why we are using a negative symbol. So according to Lenz's law, we are using negative symbol. Clear? So first law states EMF is induced. Second law states EMF is directly proportional to the rate of change of flux. To remove the proportionality, we have kept number of turns. Right. So let us do a small problem here. So here the problem is talking about a coil has 400 turns. So they said the coil is having. So here the problem is saying that a coil has number of turns, n is equals to 400 turns. Find the induced voltage or induced EMF, anything is fine. Okay, induced voltage in it if the flux changes from, so flux is changed, means derivative of flux. So the flux has changed from 0.2 milliwebers. Usually the value is 0.2 milliwebers, but it has changed to, so the change is 1 milliweber. in 0.2 seconds. It means time is also given as 0.2. So now this is the question. So we are supposed to find the EMF, means the voltage, induced voltage, when there is a rate of change of flux. Okay, so when there is a rate of change of flux, what is our formula? Actually, this is what we learned, right? EMF is N d phi by dt. So induced voltage is equals to N, right? N d phi by dt. What is d phi? Change in flux with turns to time. So it is talking in terms of time. So first let us talk about d phi. What is d phi? N is 400. Yeah, we know number of turns are 400. Perfect. Then what is our change of flux? So change of flux is 1 minus 0.2, because the flux changes from 0.2 to 1. So now it is 1. Initially it is 0.2. So 1 minus 0.2. Both are milliwebers only. So I am just saying 1 minus 0.2, right? So not to get confused, you can use milli here. So it reminds you that there is multiplier 10 power minus 3 in the problem. Okay. So 10 power minus 3. So number of turns is 400. Rate of change is 1 minus 0.2 milli divided by the time period. So what is our time period? Time period is 0.2 seconds, right? So here the time period is talking about 0.2 seconds, right? So this is 400 multiply 1 minus 0.2 is 0.8 multiply milli is 10 power minus 3 divided by 0.2. So if you do all this, okay, 400 1 minus 0.2 is 0.8, milli is 10 power minus 3 divided by 0.2. So 0.8 divided by 0.2 is 4. 4 into 4, 1600. 1600 into 10 power minus 2 will give you 1.6. So we are talking about voltage. So it is 1.6 volts. So that is the problem. Okay. So let's try another problem to further remember the formulas. So practicing these formulas will make you to remember the formulas. Okay. So next question. So the question is talking about the coil of resistance 100 ohms. So what did they say? The resistance is 100 ohms. So resistance is equals to 100 ohms. Is placed in a magnetic field of 1 milliweber. So magnetic field of 1 milliweber. So magnetic field, what do you mean by magnetic field? We just leave it like that to write the sign. Okay. The coil has 100 turns. So number of turns is 100. And a galvanometer of 400 resistance is connected in series with it. So resistance is there and it is a galvanometer. So let me say galvanometer resistance, because already we have some resistance here, which is coil resistance. So let me say coil resistance RC, galvanometer resistance RG. RG is given as 400 ohms, which is connected in series. So find the average EMF, means the voltage, and the current. So we should find the voltage and current if the coil is moved from given field to a field of 0.2. So it is moved from a given field to another field. So given is how much? 1 milliweber is moved to 0.2 milliwebers in 0.1 second. So time is 0.1 second. It means flux, right? So the change of flux is this. So d phi is given as 1 milliweber. Sorry, phi is given as 1 milliweber. D phi, the change is 1 milliweber has given to a field of 0.2, has changed, moved to, right, 0.2 in time. So this is the given data. So according to the given data, they are asking us to find the current and to find the voltage. So what is the best way? First we can do, first let us find the rate of change of current. Rate of change of flux. So the change flux is 0.8 milli, which means 0.8 into 10 power minus 3. So let us remember this point. Now they are asking us to find the EMF, induced EMF E. Induced EMF is what? Number of turns into rate of change of flux, right? So what is rate of change of flux? Rate of change of flux is d phi by dt. Number of turns is 100. d phi is 0.8 into 10 power minus 3, and t is derivative of time. Time is 0.1. So if you solve this, you will get 0.8 volts because EMF E is 0.4. Finally we got E. Then we are supposed to find I. So to find I, what we can say? V is equals to IR. V means here V is referred as E. So E is equals to IR. R means coil resistance is there, galvanometer resistance is there, right? So E is 0.8, coil resistance is 100, galvanometer resistance is 400. Therefore, I is equals to 0.8 divided by 500, which will give you 1.6 milliamps. Okay, so according to this, if you can see, resistances are given, number of turns is given, flux is given, and they said the flux of 1 is changed to 0.2. So the change of flux 1 to 0.2 is 0.8. So the change is 0.8. So that 0.8 we substituted and we found E because we know this formula. Here we are not showing minus. The reason is we are just talking about the induced EMF, but when we are talking regarding voltage comparisons, then sometimes we will take minus. So here they are just talking about EMF induced. They are not talking about the direction of the EMF induced. So I am not using minus. If direction is spoken, I will talk about negative. When they are just asking what is the value, I will just say the value. If they ask the value is in which direction, negative direction or positive direction, means forward direction or backward direction, then I will consider the symbols, right? So that's the reason I just took E is equals to N d phi by dt. So N you know, d phi you know, dt you know, you got E. Usually V is equals to IR, V means E. So E you know, I you should find, R also you know because RC plus RG is already given. So this is how you are finding I value. Okay, so now here we are supposed to talk about inductance. Okay, so inductance, mutual inductance and self inductance. Okay, so what do you mean by inductance? So before we go further, let us talk about dynamically induced EMF. Means here we are saying that EMF is induced, right? So when we said EMF is induced, how it is induced? So dynamically induced EMF. So now we are talking about dynamically induced EMF. Dynamically induced EMF. So what do you mean by dynamically induced EMF? Whenever flux linking with the coil or the circuit changes and EMF is induced in the coil, that is what we learned, right? Now this EMF which can be produced is having two ways. One is by increasing or decreasing the magnitude of current. So when you are increasing or decreasing the magnitude of current which is producing the linking flux, in this case what happens? There is no motion of the conductor or of the coil. So EMF induced in this way is known as statically induced EMF. This is statically because we are using statistics. We are increasing current, so obviously it changes. We are reducing current, it changes. So we are doing it for ourselves. Okay. Then second thing. So this is statically induced EMF. Now the second one is talking about By moving a conductor in a uniform magnetic field, and EMF produced in this way is known as dynamically induced EMF. So what is the meaning of this dynamically induced? Means when we are moving the conductor in a uniform magnetic field. Uniform magnetic field means we know that the magnetic field is aligned properly. Okay. So then we are saying we are moving the conductor in this magnetic field uniformly and EMF is produced. Okay. So this type of uniformity maintained will give dynamically induced EMF. This way of increasing and reducing the input will give statically induced EMF. Okay. So here whenever I am talking about EMF induced, here we are getting a flux which is cut per second. Okay. So this flux is nothing but the flux density with its length and voltage. So I can say that flux is equals to BLV, flux density, length and the voltage. So the rate of change of flux is BLV, which is Webers per second. Okay. So the induced EMF is d phi by dt, which is equals to BLV volts. So the rate of change of flux is EMF, right? So obviously EMF will be BLV. So that's why we said EMF induced is nothing but, because I got 100 voltage. How am I getting the 100 voltage? I am getting because of the magnetic flux density, because of the length and because of the velocity of the conductor. So these three things are giving me rate of change of flux. Because of that my EMF is induced. So this is nothing but the rate of change of flux is nothing but EMF induced. But here again we are talking about angle, because if the conductor is moved at an angle, particular angle without following the direction, so when you are moving with an angle, we can say E is equals to BLV sin theta. Okay, so the direction of this induced EMF is given by Fleming's right hand rule. So that is how we are taking the equations. So let me do a problem on this. Sorry. So E is equals to BLV sin theta. We should remember that. Okay. So now let me do a problem on this. So the problem is saying find the induced EMF in a conductor. So the question is about to find the induced EMF. Okay. In a conductor of length 150 centimeters. So I am converting it into meters as 1.5 meters. Moving at an angle of 30 degrees to the direction of uniform magnetic field of flux density. So magnetic flux density is also given as 1.2 Webers per meter square with a velocity of 60 meters per second. So length is given, theta is given, angle, flux density is given and velocity is also given. So what is our induced EMF? Right now we just learned E is equals to BLV sin theta. So what is our B? 1.2. What is our length? 1.5 meters. What is our velocity? 60 meters per second. What is our angle? 30. So it is sin 30. So if you solve, you should get 54 volts. So that is the problem. Okay. So let us see another problem. A conductor of active length 30 centimeters. So length is 30 centimeters. It means we should convert it into meters. This is the major problem. Most of the people will do mistake. Centimeter should be converted into meters. Always we follow meters. Okay. So current in the coil is 100 amps and lies at a right angle. So here they are talking about the angle as right angle to a magnetic field strength. So the angle is right angle with a magnetic field strength of 0.4. So the magnetic field strength is 0.4 Webers per meter square. Calculate the force in newtons exerted on it. So we should find the force for, if the forces causes the conductor to move with a velocity of 10 meters per second. So velocity is also given as 10 meters per second. Calculate, so we should find force. So first they are saying calculate EMF induced in it. Okay. Second, the power in watts. So they want to know the EMF and they want to know the power injected. So length is given, current is given, flux density is given. So obviously we can find the force, right? Because we know F is equals to BIL. So I am saying it as F is equals to BIL, means 0.4 multiply 100 multiply length is 0.3. So you will get F 12 newtons. Perfect. Okay, velocity is given. So now the question is E. E is equals to what? BLV, right? So BLV means, that is what we learned, BLV. I am not writing about sine theta because they said it is right angle. So 90 degrees sine 90 is 1. So we are just, as they said it is a right angle, we are just considering it as BLV. Okay. So BLV means B is 0.4, length is 0.3, velocity is 10. So you will get 1.2. And the second question is power. So P is equals to VI. This is the formula you know. V means E. I is given as 100. So E you got is 1.22. So 1.22 into 100, which is equals to 120 watts. So that is power. This is voltage. This is force. So this is how you can calculate. So just trace the formulas required for each. So trace formulas at one page. So it will be easy for you to understand, to remember and to solve the problems. Okay. Yes. So next, our next question is about self-inductance and mutual inductance. So what is this about? So if there is an inductor, okay, like this, I have let current to pass through it. So obviously what happens when a current is passed through a coil, it will produce an EMF, means voltage, right? So voltage is directly proportional to current, but rate of change of current, because the current will be given continuously, EMF will be producing, right? So voltage is directly proportional to di by dt. So to remove the proportionality for the inductor, I am saying V is equals to L di by dt. According to Lenz's law, I can even say minus L. Okay. So V is equals to minus L di by dt. Okay. So here same way V can also be written as number of turns with rate of change of flux. That is what we learned in our previous concepts, with a negative symbol. So voltage is nothing but inductance with a change of current, or number of turns with a change of flux. So it means I can equate these two. So when I equate these two, what will happen? Minus L di by dt is equals to minus N d phi by dt, right? Negative, negative I can cancel. Di by dt I can cancel. So L into I is left, N into phi is left. Therefore, inductance is nothing but number of turns into flux by current. Okay. So this is the formula. So this inductance is called as self-inductance. Why are we calling it as self-inductance? We are taking an inductor, we are giving a current in it. So whatever is produced in it is the self one. So that's why this is a self-inductance. Then now let us take another scenario where there are two coils coupled. Okay. Now when a current is applied to one coil, what will happen? Right. So when a current is applied to one coil, what happens? I1 is the current given to it. Here number of turns is N1. Here number of turns is N2. Okay. So then because of the current produced here, there is a flux induced. So because of the current 1, in coil 1 flux is induced. because of current 1, in coil 2 also flux is induced. Okay, so here also I can write, so here the voltage will be, the final output will be what, V2, because current is given, these are coupled, so final output is received on the second hand side. So secondary side when I am receiving, it is V2. So I can say V2 is equals to minus L di by dt, but instead of L I am writing M. The reason is, here I am writing L because it is self inductance, because of one coil its own inductance, so its own L. But here because of one coil, another coil is producing an output, so there is a mutual inductance between these two. So that's the reason I wrote M. I can't just say single inductance, because these two mutually added and acted to produce V2. So the output is nothing but the mutual inductance with a change of current. Which current? I1 current. Okay. So same way I can write V2 is equals to minus number of turns in the second coil, because output belongs to second coil. So number of turns also belongs to second coil with the change of flux. Flux in the second coil is 512 because of current 1 in the second coil. So 512 by dt. So I can equate these two, right? So minus M di1 by dt is equals to minus N2 d512 by dt. Negative negative cancel, d by dt cancel. It means M I1 is equals to N2 512, right? So I can say mutual inductance M is equals to N2 512 by I1. So M is called as mutual inductance. So if I want to know what is the inductance of a transformer, because it will have two inductances, right? So like that, if I, whenever I want to know what is the mutuality between the inductors, then I can use this formula, mutual inductance. Here you can see N5 by I. This is also N5 by I. But N and 5 belongs to secondary circuit. I belongs to the primary circuit. Now, let us take another scenario. So, in another scenario, this is one inductor. This is another inductor. Another coil. Okay, inductor or coil, anything is fine. So, current is given in this coil. Then what happens? Same. N1, N2 turns are there. Because of I2, V1 will be produced. Right? So, flux because of the second in second, because of the second in first, flux will be induced. So, here I can write it as, here what I can write, V1 is nothing but minus M d I2 by dt, which is also written as minus N1 d 521 by dt. Okay, so minus minus cancel, d by dt cancel. It means Mi2 is equals to N1 521. Therefore M is nothing but N1 521 by I2. So therefore I can say self inductance is N5 by I. Mutual inductance is N2 512 by I1 or N1 521 by I2. So this is my self inductance and this is my mutual inductance. So when a single inductor is there, a single coil is there, I will use this. When there is double coil with like double inductances, then I will use mutual inductance, self inductance and mutual inductances. So these are self inductances and mutual inductance in the unit. Okay. So here I am talking about this formula. So let me try to do a problem on this. Okay. So the question is saying a solenoid has 1200 turns and carries a current. Okay. So solenoid, what do you mean by solenoid? What is the meaning of solenoid? So the meaning of solenoid, it is nothing but a cylinder coil of wire acting as a magnet. Okay, so it is also a magnet which is carrying an electrical current within it. It's a type of electromagnetic coil. Okay, so they are saying there is a coil and the number of turns in the coil is given as 1200 turns. So a solenoid has 1200 turns and carries a current of 2 amps. The iron core has a length of 0.4 meters and cross sectional area of 80 centimeters square. It means we should convert it into meters. So 80 centimeters means 0.08 meters centimeters square. So it means meters square. The relative permeability is 1000. So here the relative permeability is specifically given, so we should make note of it, so which is 1000. So now they are asking us to calculate the self-induced EMF if the current is switched off in 0.01 seconds. So we need to find self-inductance and the current is 0.01 sec. Okay, so actually what is the formula we are considering for self-inductance? So self-inductance is nothing but N phi by I, right? So here N phi by I is the formula which we are using. So they are asking us to find the induced EMF with finding the self-induced EMF. Okay, so EMF induced. So EMF induced with the help of self-induced EMF. So finally we need to find is E. So we know E is equals to L di by dt, right? So to know that di by dt, what is di by dt? So just this is another part. So what is di by dt? With terms to time change of current. So what is the change of current? Current is 2. It's always 2, right? There is no change in the current according to the question. But the time period is given as time as 0.01 seconds. So 0.01. So 2 by 0.01 is 200 amps per second. So di by dt, we know di by dt. Now we should know L. So to know L, we write N phi by I. N, yes I know. I, yes I know. But phi, I don't know phi. But phi is in given terms of length, area and mu r. So for that I am going to say that phi is equals to, okay, so phi is equals to N, usually phi means flux, right? So flux in self-induced EMF is given as number of turns into current in the coil by length by mu naught mu r a. Okay, so this is general formula for flux in terms of number of turns and permeabilities. Okay, length and area. So you should remember this formula. I know this is little hard, but you need to practice this formula. So according to this, I can say L is equals to N by I multiply Ni. So this thing I can send it to denominator, right? Numerator, right? So Ni mu naught mu r a by L. I cancel, so N square is there, right? So N square mu naught mu r a by length. So this is the formula I have. N square, N I know, mu naught, yes, 4.2 10 power minus 7, mu r is given as 1000, A is given as 0.008 m square and length is given as 0.4, right? So by substituting all this, you should get an answer 36.1 Henry. So just remember that whether you are getting it or not. So therefore I can say induced EMF is L di by dt. L is 36.1 and di by dt is 200. So you are supposed to get 7238 volts. So this is the formula. So this is how we will find the self inductance. So here we are talking about inductances. So in the inductance we are talking about self inductance and mutual inductance, how the coils are there. So what are the formulas and how to do problems on that to find the EMF induced. So this is about Faraday's laws of magnetic induction. Here we are talking about transformers and generators. The purpose of talking about transformers and generators is because transformers follow the Faraday's law according to this. So usually a transformer is having coils like this, right? So here we are giving a current. So the magnetic field is produced here, right? So the induced voltage in the secondary coil is given as V, and this here also, when a changing voltage is applied to the primary coil, the back EMF generated by the primary is given, right? And here the secondary is given, means V1 and V2. That is what we learned in Faraday's law. So the same Faraday's law we are applying for the transformers. So transformers and Faraday's law. So depending on transformers only Faraday's law is working. Sorry, depending on Faraday's law only transformers are working. Okay, and even the generator. So a generator, generally what happens? It can transform mechanical energy into electrical energy, right? So this is a generator. Same way, an electric motor, which is also a device for transferring electrical energy into mechanical energy. An electrical generator does the reverse. Like motor, which can convert electric to mechanical, generator makes mechanical to electrical. At the heart of both motors and generators is a wire coil in a magnetic field. So the same device can be used as motor or generator. So when the device is used as a motor, a current is passed through the coil. The interaction of the magnetic field with the current causes the coil to spin. So to use the device as a generator, the coil can be inducing a current in the coil, and this is the alternative current which is induced. Same way, motor also, like generator also, in a reverse way, it is talking about how it is converting how it is converting mechanical to electric. Okay, so whatever it is, they are talking about magnetic fields. In the magnetic fields, because of the Faraday's laws, the force, the induced EMF is induced, and those EMF, how they are induced, all these things are known by the Faraday's first law and second law with application of Lenz's law. So these are the things which we learned from this concept. Clear?